Hi everyone. So today's workshop, we're going to be going over organic chemistry. It's mostly like an introduction to nomenclature of alkanes, alkenes, alkynes. And then right after, we're going to get right into identifying some more of the important functional groups that you want to be able to recognize. So let's get started. So a quick little recap. A lot of organic chemistry is going to be communicating using bond line structures. And so bond line structures, basically, if you were to draw the Lewis structures of every single molecule, it's going to take way, way too long. And it's going to be tedious and it just overall a pain to draw. So instead, what we're going to do is we're going to convert this structure of, say, like this molecule, amoxicillin. We can instead represent it in bond line structure or skeletal structure, such that it looks like this compound on the right. You can see it right here. And as you can see, it's a lot more clean and it's a lot easier to read for the reader. And it actually just represents the exact same compound. So that way we don't have to show these hydrogens, we don't have to show the carbons. The only hydrogens that you would really show are the ones that are attached to, or the hydrogens that are of interest. So like on functional groups or particularly reactive hydrogens. So what's happening here is if we compare this left structure of amoxicillin to the right structure, which is in bond line, we can see here that we don't actually visually see this carbons here. So like there'll be a C right here. There's also going to be a C right here. You could see a carbon right there, and here, and here, and here. And basically at every single junction or like bend, that basically represents a carbon. And we also don't show the hydrogens because when we draw these structures, we're going to assume that we're going to make 4 bonds to each carbon. So let's take this carbon, for example. This very top one that I've highlighted in yellow. There is 1 hydrogen that is implied. So it would kind of look something like this. And that is because if you compare the structure from the left to the right, the hydrogen is we're only going to add 1 because this carbon already has a total of 3 bonds without the hydrogen. So 1, 2, and 3. And then we can fully saturate that carbon by adding in that final hydrogen. So it's going to be like this. And I guess saturate isn't really the proper term. It's more like we just fill the carbon such that it makes 4 bonds every time. So if we compare like another one, let's say we're looking at this particular junction. If you compare it to this carbon right here, we can see that there's no hydrogens attached. And that makes sense because if we look at it, there's already 4 bonds to this carbon. And so there's not going to be a hydrogen shown here because it already has 4 bonds and 4 connected atoms. Whereas if we look at a terminal carbon, so like let's look at this one, and we compare it to the one right here, this carbon only has 1 bond to another carbon, or 1 bond to another molecule, or actually 1 bond to another atom. So then we will just end up drawing the proper amount of hydrogen such that the carbon would make 4 bonds total. So that's how we get 4 hydrogens attached to it. And that's basically bond line structure. So the next part is the parent chain. So being able to identify what the parent chain is very, very important. If you can't quite grasp what these are, like the methyl or ethyl, propyl, but, pent, hex, hept, oct, non, and dec, it's going to be very, very difficult to communicate between other chemists around you, because a lot of times they'll be using this type of terminology, and then it's very hard to understand exactly what molecule they're talking about. So as you can see here, after 5, starting from around 5 to like 10, or maybe even like 12, it's the naming system is pretty similar to how you would name something like tetraoxide or like uh tetrafluoride or something like, or pentafluoride. Um, it just goes pentafluoride or like hexafluoride. So just pent, hex, hept, oct, non, and dec. Those just represent 5, 6, 7, 8, 9, and 10. The only difference is 1 through 4. We represent them differently. So instead, we'll do meth for 1, eth for 2, prop for 3, and bute for 4. And then the alkane that goes along with it will be methane, ethane, propane, and butane. So some general reminders for naming simple alkanes. So you'll want to follow 4 general steps whenever you want to name a simple alkane. So first, you're going to want to identify the parent chain. So the parent chain, if you go back to our previous slide, it's just going to be the longest possible carbon chain that goes uninterrupted. Then you would want to name each substituent. And so a substituent would be anything that is attached to the parent chain. And then afterwards, you want to number that parent chain and then assign a locant for each substituent. So what that means is, let's say we take this bottom example, cyclopropane, and let's say we had like a branch hanging off of it. What I'll do is I'll number each carbon in that carbon chain and then assign a locant. So on the 1 position, there is this methyl group hanging out. And that's basically what that means. And then afterwards, at the very end, you'll want to arrange the substituents in the name alphabetically. However, if the alkane is in a cyclic shape or like a ring, you'll want to add the prefix cyclo. So if we look at these bottom examples, going back again, so we have cyclopropane. If you look at our previous slide, prop means 3. So prop means 3. And then ane means that we are working with strictly an alkane. So there is no double bonds or triple bonds, which I'll go into in a moment. And then cyclo at the beginning indicates that the 3 carbon chain forms a cyclic shape. So you can see this is like kind of like a circle. Well, it's like a triangle, but it closes basically. And so that's what they call cyclo. The next one is pretty similar. If you remember from the previous slide, bute means 4. Ane means we have an alkane, and cyclo means that the carbons in the butane form a cyclic ring. So you can see 1, 2, 3, 4, and then they all just joined together. Another one, pretty similar. Once again, pentane. Pent means 5. Ane means we have an alkane. Cyclo means that it forms a cyclic shape. So if you count the carbons, 1, 2, 3, 4, 5. It's a 5 carbon chain that forms a cyclic ring. So a little practice. Try and name some of these following compounds. I'm going to go over the first 2 so that there's like a general idea of how this works. And then afterwards, you guys can try out the remaining problems. So this first compound, we have this chain right here. We can tell it's an alkane because there's no double bonds. So the first thing I'm going to do is identify the parent chain. So the parent chain is always going to be the longest uninterrupted chain that also maintains the highest priority in terms of functional groups. So I'm going to count 1, 2, 3, 4, 5, 6. So we know that a parent chain is a 6-carbon chain, which means we have hexane. And next, we're going to want to count to see if there's any substituents. In this particular example, there is no substituents. So the name of this compound right here would just simply be hexane. Now, what about this next example? We have this carbon chain. We're going to want to identify the parent. So I'm going to do 1, 2, 3, 4, 5. So 5-carbon chain means we have pent, so pentane. Next, I'm going to want to number each carbon. So I'm going to do 1, 2, 3, 4, and then 5. And then identify these substituents. So we can see this is going to be a methyl substituent right here, meaning that we have 1 carbon hanging off here. Our carbon is a CH3 in this case. So I'm just going to write down 3-methyl on the top. And then, so this is going to be our substituent. We're just going to throw it onto the main part of the name. So I'm just going to put 3-methyl pentane. So the substituents need to be alphabetical. And it'd be better if these were one word together. No hyphen or no space. So I'm actually going to go over one more. So let's try out this next one. So I'm going to want to identify the parent chain once again. So there's a few options for our parent chain, and both of them should be valid. So I can do this as one parent chain, 1, 2, 3, 4, and 5. So that would be a 5-carbon chain. However, I could also say this is going to be the parent chain, 1, 2, 3, 4, 5. So the next thing I'm going to do is I'm just going to number the carbons. In this particular example, it won't matter which direction you choose. In the future, you would want to choose a direction that gives the substituent the lowest number, the first substituent the lowest number. So I'm just going to label these 1, 2, 3, 4, and 5 again. And then I'm going to identify each substituent. So I'm going to say there's going to be a 2-methyl. There's also a methyl at the 3rd position. And we also have a methyl at the 4th position. So I'm going to put that one up here. So this is a 5-carbon chain. I'm going to say that this is going to be a pentane. And then we're going to want to throw in all the methyls all together in that one name for the substituent. So what we can do is I can indicate those substituents as 2, 3, 4, and then trimethyl. So it'll be 2, 3, 4 trimethyl pentane. It's going to be the name of this compound right here. And if you were to go in the direction where I chose the green as the parent chain, you would also realize that these substituents actually landed on the same spot. So there's also going to be a methyl hanging off the 2, the 3, and the 4 in that case. So try out this next compound on the very right corner, top right corner. I'm going to go over it in a moment. All right, so I'm going to go over this top right corner. So I'm just going to identify the parent chain once again. I'm going to go 1, 2, 3, 4, 5, and 6. Another parent chain you could do is 1, 2, 3, 4, 5, 6. So these are both valid parent chains. In this particular example, one is not better than the other again. So what I'm going to do is I'm going to number the carbon chain, and I want to go in such a way so that it hits alphabetical first, since the substituents are both tied in this case. So I'm going to go 1, 2, 3, 4, 5, 6. Or you could have went 1, 2, 3, 4, 5, and 6 again. So if we label these substituents, we have a ethyl group hanging off the 3. So I'm going to write 3-ethyl on top. We also have a methyl group hanging off the 4. And it's a 6-carbon chain, so I'm going to write hexane. And basically, I'm going to throw in these substituents and make sure they're alphabetical. So I'm just going to do 3-ethyl, 4-methyl. So the final compound name would be 3-ethyl 4-methyl hexane. This next one on the bottom left corner. So I'm going to identify the parent once again. So I'm going to find out this is going to be the parent. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be an 8-carbon chain. That'll be oct. So I'm just going to number it. And it's always a good idea to number these so that you don't lose track of your carbons. So this is going to be an 8-carbon chain. I'm going to look at these substituents. It doesn't matter which direction that I numbered it in this case, since it is symmetrical. So I could say that on 4 and 5, we have an ethyl group. We have 2 ethyl groups, so I'm going to indicate that as 4,5 diethyl. And now I'm going to identify the next groups is going to be methyl groups hanging on the 3 and the 6. And there's 2 of them, so I'm going to do 3,6-dimethyl. And then the parent chain, octane. And I don't need to worry about alphabetical because I just so happen to have written it in such a way that the ethyl comes before methyl. So it is already in alphabetical order. The next one is going to be a cyclic compound. So I'm going to count the number of carbons. So I'm just going to start numbering so that I don't have to highlight the parent chain. So I'm just going to do 1, 2, 3, 4, 5, 6, and then 7. A 7-carbon chain is going to be hept. So it'll be heptane. Remember that it is in a cyclic ring, so I'm going to do cycloheptane. And then the substituents, there's going to be 2 methyl groups hanging off the 1 carbon. So I'm going to write 1-methyl. And then for my own, just my personal preference, I like to write 1-methyl again, because that indicates that we have a methyl hanging off the first carbon again. And we chose 1 because it would give it the lowest substituent number. So in the parent name, I can indicate this as 1 and then comma 1 to indicate that the first carbon has a methyl twice. And I'm going to put dimethyl to indicate that we have 2 methyls, cycloheptane. This next one is pretty large. This is going to be a 6-membered cyclic ring in this case. What I'm going to do is, let's see. So cyclic compounds usually will be the parent chain for simple alkanes. So I'm going to do a 6-membered ring. That will be cyclohexane. I'm just going to number it. So I'm going to choose this top part as my 1 position. And I chose that because if we put the 1 up there, it will give the substituents the lowest possible numbers. For example, because we have 2 methyls on the 1 position. If we put it on any other position, the first carbon, the total number of the substituent numbers would be a lot higher. So what I'm going to do here is I'm just going to count each methyl hanging off the parent chain. So I'm going to say there's 1, 2, 3, 4, 5. So we have 5 methyl groups. We also have 2 ethyl groups hanging off the parent chain. So we have this ethyl and this ethyl. And ethyl comes before methyl alphabetically. So I'm just going to say on the 3 and the 5, we have 2 ethyl groups hanging out. So I'm going to indicate that as 3,5-diethyl. Next, we have a methyl group hanging off on the 1 again, the 2, the 4, and the 6. So I can indicate all those methyls as 1, 1, 2, 4, and then 6, or not 6, 6 and then dash pentamethyl. So then the final name is a little bit squished up here. So the final name would be 3, 5 diethyl, 1, 2, 2, 4, 1, 1, 2, 4, 6 pentamethyl cyclohexane. This last example, don't let the long chain on the bottom throw you off. Instead, you'll want to choose this as the parent. So don't say that the parent chain will be hexane in this case. Instead, I can say the parent chain is going to be cyclobutane, because this is going to be a 4-carbon chain. So I'm going to write cyclobutane as the parent. And then on the 1 position, we have this 3-carbon chain that is going to be a propyl group. And then on the 1 position again, we have an ethyl group hanging off. So remember, the propyl means 3 and ethyl means 2. So I can indicate it as 1 ethyl because an ethyl group is hanging off the first carbon. And then I can put 1 propyl because on the first carbon, there's also a propyl hanging off of it. So the final compound name would be 1 ethyl, 1 propyl cyclobutane. So the next exercise is just going to be drawing compounds based on a name. I personally find it is a lot easier because there's a lot less error for like drawing the compound compared to finding out the name. So what I'm going to do is first, I like to identify the parent. So the parent is going to be nonane. So I'm just going to draw a 9-carbon chain. So I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to label the carbon chain. And so on the 4th and the 5th carbon on this chain, we have ethyl groups hanging off of it. So I can just draw an ethyl group hanging off the 4th position. That'll be a 2-carbon chain. On the 5th carbon, we also have another ethyl group hanging off of it. So 1, 2, that's another 2-carbon chain. On the 2nd carbon, we have a methyl group hanging off. And on the 6th carbon, we have a methyl group hanging off. And that's basically what that compound will look like. You can tell it's a lot easier to draw the compound from the name rather than find a name based on the drawing. So try the second one. It'll be 1, 2 diethyl. 3, 4, 5, 6 tetramethyl cyclohexane. So the first thing I'll do is we see cyclohexane. That's going to be our parent. So I'm just going to draw a 6-carbon chain in a circle or in a cyclic shape. I'm going to number my carbons. So I'm going to do 1, 2, 3, 4, 5, 6. And on the 1 position and the 2 position, we have ethyl groups hanging off of it. So I'm going to just draw, that's 1 carbon, 2 carbons. On the 2nd carbon, once again, I'm going to draw an ethyl group, 1, 2. And then on the 3, the 4, the 5, and the 6, we have a total of 4 methyls, so tetra. So each one of those locants has a methyl group hanging off of it. So I'm just going to draw methyl groups hanging off of each one. So I have 1 here, 1 here, 1 over here, and 1 here. And so that's what this compound would look like. So yeah, hopefully it's a lot easier to draw the compounds given a name rather than the other way around. Okay, so alkanes and alkynes. So they're very, very similar to alkanes. The only difference being that they have a carbon-carbon double bond or a triple bond somewhere in the molecule. And alkanes and alkynes, they'll generally have more priority than alkanes whenever you name them. And you want to start in the direction that would give the double bond the low, it would give the double bond or triple bond the lowest number. So we don't really care all that much about the substituent number as much as we do about the pi bond or the double triple bond number. So if we look at these examples here, they numbered the carbons from left to right. So this is going to be the parent chain highlighted in blue rather than, say, going in this direction. They don't choose it such that it goes in this direction because you want to give the alkene the smallest number. This bottom example, you might think that this could be the parent chain because it's a very long carbon chain, 1, 2, 3, 4, 5, 6, 7. That would not be the case. You would actually prioritize giving the alkene the lowest number. So this would be the parent chain. So we have a 5-carbon chain, so that would be a pentene. So a little practice. I'm going to go over one example, and then hopefully you guys can try out the rest. So this first one, we have an alkene because we see a double bond right there. What I'm going to do is I'm going to number the carbons in such a direction that it will give the lowest alkene number. In this case, if you actually counted, we do 1, 2, 3. And if you go in the other direction, it's 1, 2, 3. So it's actually tied. And so since there is actually a tie, what we're going to do is we're going to count the substituent number instead. So this substituent of methyl is going to be a lot smaller than this methyl substituent. So because of that, we're going to choose from right to left as our parent chain. So we can choose like 1, 2, 3, 4, 5, and 6. Or we could also put this as our 1. In this case, it wouldn't change the name because no matter what, there's going to be a methyl hanging off the 2. So what I'm going to do is I'm just going to, once again, identify these substituents. So on the 2 and the 4, we have methyl groups hanging off of it. So what we can do is 2, 4, and we have dimethyl. And this is going to be a 6-carbon chain. So I'm going to do, before that, actually, I'm going to want to indicate where the alkene is. So the alkene is on the 3rd carbon. So to indicate that it's on the 3rd carbon, what we can do is I can put 2,4-dimethyl, and then 3 to indicate that's where the alkene is going to be. And then we'll say 3-hexene. And that would actually be the name of the compound. We're just going to ignore that there is actually going to be another thing that we can indicate to make them more specific. We can say that there's an E and Z, but I'm not going to go into that for this workshop. So there's actually another way you could write this compound. You could also write it as 2,4-dimethyl. And then we could write hex and then 3 to indicate that's where the alkene is. Hex 3-ene. So this is an alternative way to write that compound, but they represent the same thing. So let's go over this next example. I'm gonna once again number the carbons. 1, 2, 3, 4, 5, 6, 7. So we have a 7-carbon chain. 7 is hept, so I can write heptene. The alkene starts on the 3rd carbon, so I'm going to write 3-heptene. And then on the 5th carbon, we have a methyl group hanging off of it, so I can write 5-methyl. Heptene, and that'll be the final compound name. The next example, this one right here, I'm going to find the parent chain. It's always going to be the one that gives the alkene the lowest number. We wouldn't want to go in this direction. Instead, it'd be better to go in this direction for our parent. So if we go in that direction, we have 1, 2, 3, 4. That'll be a 4-carbon chain. So we can indicate that as butene. The alkene starts on the 1st carbon, so I can put 1. And then on the 2nd carbon, there's this whole ethyl group hanging off. So I can write 2 ethyl, 1 butene. That would be the compound name. This next example on the bottom, we see it looks like a square with an extra line in it. This is going to be a cyclo alkene. So this is going to be a 4-carbon chain. So I can write cyclobute. Remember that there is a double bond right here. So this is going to be an alkene. So I'm going to write cyclobutene. And you don't have to indicate where the butene is in this case. It's implied that you would start either here or here. So it's just going to be like saying 1 cyclobutene, but you don't have to show the 1 unless there's actually substituents on it. So like if there was a substituent of a methyl hanging off here, you'll show like 1 3-methyl cyclobutene. And you always assume that the double bond is going to be the 1 position on the chain. This next example, we have a 6-carbon chain. It looks like a hexagon. So we have an alkene here. We can indicate that as cyclohexene. This is the last example. This is going to be a triple bond. A triple bond is not alkene. It's going to be an alkyne. So what we can do is we can just number it once again. And it may look unusual, but alkynes are typically drawn straight. Drawing them a triple bond like this is not really an accurate representation because the orbital overlap causes it to be straight. So you want to draw these alkynes as straight lines. So if you were to do the name on this one, we would say that the parent is going to be a 2 pent, because there's a 5 carbon chain. So 2 pentyne. And then on the 4th carbon, we have 2 methyl groups hanging off of it. So I can put that as 4, 4 dimethyl, and then 2 pentyne. And that'll be the name of this compound. So now we're just going to be drawing compounds. Once again, I personally find these a lot easier. So the first one, we have 2,3-dimethyl 2-pentene. Pentene means we have a 5 carbon chain, and it's going to be a double bond somewhere. So I'm just going to draw 1, 2, 3, 4, 5. And I'm just going to number it 1, 2, 3, 4, 5. And then that means on the 2, we have an ene. So 2, we have an alkene. So I can just draw a double bond here. And then on the 2 and the 3 position, we also have methyls hanging off of it. So I can indicate it like this. I'm just going to draw a methyl hanging off the 2 and a methyl hanging off the 3. And that's what 2,3-dimethyl 2-pentene looks like. The next one is a little bit more challenging. You can see I changed the way that I wrote it. There's going to be a 4-ene and then a 1-ine. That means this compound is going to have both an alkene and an alkyne on it. Hex indicates that we have a 6 carbon chain. And so I'm just going to draw a simple structure like this first. 1, 2, 3, 4, 5, 6. I'm going to label it 1, 2, 3, 4, 5, and then 6. And so on the 1 position, we have an ine, meaning we have an alkyne. So I'm going to draw a triple bond right here. On the 4th position, we have a double bond because ene. And then on the 3rd position, the 3rd carbon, we have a methyl group hanging off of it. And so this is what our structure is going to look like. However, you don't want to show triple bonds like that. You want to draw triple bonds straight. So I like to draw it like this, and then I like to rewrite it. So what you could do is you could do a triple bond right here. This is going to be the 1st carbon, 2nd carbon, 3rd carbon. So on the 3rd carbon, we have a methyl group hanging off of it. This is going to be the 4th carbon. There's a alkene right here. And then the 5th carbon and the 6th carbon. So the structure on the bottom is a more accurate representation of what 3-methyl hex 4-ene 1-ine looks like. So moving on to the second part of this workshop, it's going to be functional groups. And so functional groups are another thing you definitely want to be familiar with and be able to recognize. They affect both the physical properties and the chemical properties, so like the reactivity of each molecule. And so here are a few examples. There's actually a lot more, but here are some of the more common ones that you might see. So we can see there's alkanes. That's just what we've been drawing in the previous slides. Alkenes, once again, and alkynes, we've been drawing those. This ring right here, the cyclohexane with alternating double bonds, is an arene, or they also call it like an aromatic ring. And R, which means any carbon or hydrogen, in this case, it's going to be more likely a carbon in most cases, bonded to a halogen. X means you have an halo alkane. An aldehyde looks a lot like this one right here. Ketones is pretty similar. However, there's no hydrogen on the end of it. There's an alcohol is ending with an OH hanging off. An ether is an oxygen bonded to two R groups. An amine is a nitrogen bonded to an R group. Carboxylic acids are basically going to be like a ketone, but also has an alcohol connected to it. A acid anhydride is this big molecule. It kind of looks like an ester, which is to the right of it. But instead there's an extra ketone or carbonyl group next to it. An amide looks like a carboxylic acid, but instead of an alcohol, it has an amine on it. And an acyl halide looks like an aldehyde, but instead of the hydrogen, you have a halogen bonded to that position. So you want to be able to recognize some of these on some compounds. So here are some examples. So we're going to identify some possible functional groups that you may find in some substances that you might see around your house. So this first one, we have acetyl salicylic acid. This is also known as aspirin. So if you were to identify some of the possible functional groups, we could say that right here, we have an arene. You could say that this is a ketone, but that would not be completely accurate. More specifically, you could say that this entire group right here is an ester. And then there's also one more group down here. This is a carboxylic acid. Now this next one, caffeine. So it's like in your coffee or like in tea. There's actually multiple ways you could interpret this. You could potentially say that this is an amine, and this is an amide, and this is a ketone. How I saw it is this is one amide. This is actually another amide. And then right here we have an amine, and right here we have an alkene. So these two, I consider them as amides. This is going to be an amine, and this will be an alkene. This next one is acetaminophen. You may more commonly notice as Tylenol. So once again, we have an aromatic ring. So I'm going to call this an arene. Right here, we have an OH hanging off of it. So this is an alcohol. And right here, we have this amide group hanging off of it. This last one is acetoephedrine. So this is kind of like in your medication that you might take if you had like a cold. So we have an arene. We have an alcohol here. And finally, we have an amine. And so there's just some common functional groups on some common household substances that you might find in either your medicine cabinet or in your kitchen. So this last example, This is a little bit of practice. So try and identify as many functional groups as you can and try to be as specific as possible. So I'm going to give you a moment to try it out. All right, so let's see. I'm going to start from the bottom and I'm going to work my way up. So first I'm going to see there's this N right here. This is an amine. You could be more specific and call a tertiary amine. So we can indicate that by putting a 3 and like a degree sign, meaning that it is a nitrogen bonded to 3 other atoms that are not hydrogens. We could classify this whole group right here as an amide. We could classify this one as a ketone. There's one right here. This is a carboxylic acid. There's one right here. This is an ester. Right here, we have an ether. Over here, we have an alkene. We have a aromatic ring right here, so an arene. Down here, this was not one of them that I showed on the list. This is a nitro group. Over here, we have an alcohol. We also have a alkyne right here. And finally, this may not look like an aldehyde, but it is actually an aldehyde. And that's because if you remember the rules for bond line structures, we assume that there's going to be a hydrogen added to each carbon so that every carbon has 4 bonds. So if you draw this carbon right here, there's only 3 bonds. So we can assume that there's actually a hydrogen right here. And because of that, that makes it technically an aldehyde. And so yeah, that's actually basically it. Hopefully this was a helpful workshop. And if you guys have any questions, you can always schedule for tutoring. And if you haven't already, you can join the virtual STEM Center. And you can always email us and connect with us on social media.